If you've ever visited the libraryofbabel.info, you know how amazing it is to see the short story being brought to life. A near infinite library, fully accessible on your computer. You can literally pick up and read any of the countless books within. Have you ever wondered how it's possible? Or maybe if it's actually all a big trick? I did. So last year I made a website called Archives of Pandemonium, my own version of the so-called Library of Babel. Along with it, I created a video where I tried to explain how it worked. Lots of people have asked more in-depth questions about it, so I thought it was about time I made an updated version, so here we go. If you want to pause the video and check out what we'll be talking about, go to archives.oneyeru.com. Let's start out by talking about the source material. Library of Babel is a short story written by Argentine author Jorge Luis Borges about a universe which is basically just a huge library. In this library, every possible 410-page book exists somewhere. This world consists of a huge array of hexagons. 4 of the walls contain a bookshelf, each containing 5 shelves per wall and 32 books per shelf. Something I particularly liked about the story is all the people trying to find meaning within the library. Presented in the story, it seems meaningless, since every possible book exists there. Whenever you find a book that says one thing, another exists that says the opposite. But if you think about it, every possible page of letters could also exist in reality. It's just that no one has written them down yet. And yet, when you read a century-old book in real life, you do get meaning from it, even though there's no way of knowing what the author actually meant with it. You can only go by the meaning you interpret from it, just like the people in the story. But let's say you wanted to completely prevent people from interpreting anything from your writings at all. You might want to encrypt your writings. One example of this is the Enigma machine, used by Germany during World War II, to send and receive encrypted messages. Trust me, this will be important knowledge in a second. Simplifying a bit, it basically worked like a typewriter, but with all the labels on the keys shuffled around. You type something, but out comes gibberish. Only if you had the exact same configuration of the keys could you figure out what that gibberish meant. These days, we can encrypt messages using modern computer technology, and it turns out that might have more to do with the Library of Babel than you'd think. So how did Jonathan Basile make libraryofbabel.info? Is it actually fake, like everyone seems to think it is? The answer is no, sort of. Basile explicitly says on the website that every possible page exists in the library. You can enter the address for it and get the same page loaded up every single time. This of course means that, contrary to popular belief, you can't actually see every single book on here, since every unique page only exists once. Furthermore, Basile definitely didn't store every page in the library on a hard disk somewhere in the real world. With 29 different letters to use and 3,200 letters per page, that's a lot of unique pages. That's a number with more than 4,600 digits. And since every letter takes 1 byte of storage, each and every one of those pages would take up around 3 kilobytes of storage. So he definitely didn't do that. So how can it still be true that, quote, every possible permutation of letters is accessible at this very moment in one of the library's books, only awaiting its discovery? What if there's a shortcut? Since a lot of the lines on the pages are duplicates, you could just say, have a copy of each unique line stored, and then when you want to read a page, say, I want a book that contains line number 5, then line number 781, then line number 5 billion, and so on. In fact, you could do it even better. What if Basile only stores 1 copy of each letter on his server? That's just 29 bytes, and then all you have to do is enter the exact combination of letters you want. I want letter number 19, then letter number 15, then letter number 1, and so on. But the letters aren't in alphabetical order, so you don't know what you're gonna get. It's actually just like if you sat me down with the Enigma machine and you started saying random letters. I'd type them in, then I'd give you the paper which is full of gibberish. Or you could just let me press A over and over and see what comes out. Or tell me to change the last A to a B and see if what comes out was more interesting this time. That's essentially what's going on when you're asking Library of Babel to read a specific page. When you choose a specific hexagon, wall, shelf, book, page, you're actually choosing a sequence of letters that's just as long as the page you end up reading. It's then put through an Enigma-like algorithm, which becomes the page content. Earlier, I said that the point of encryption is to prevent people from interpreting something from your writings, but that's exactly what makes the Library of Babel concept interesting. If we used a regular typewriter instead of an Enigma machine, you would enter a string of letters and get the exact same text back. Suddenly, reading meaning into it doesn't seem as appealing when going forward one page produces the exact same result with only one letter difference. You can also search on Library of Babel. How do you do that? Does the website then look at every single page until it finds what you searched for? Of course not. It just fills in the blanks and then puts it through a reverse Enigma machine, which tells you exactly what to put in to get what you searched for back. Okay, so the Library of Babel uses math to calculate the contents of the page to show you, based on the address you chose. Video over, right? Not quite. I wanted to make my own version to really find out how to do this in practice, but also to solve some narrative problems I have with the original story. You see, Basile did an extremely good job of staying true to the original story. Almost too good of a job. There are 410 pages per book, and the books are organized into shelves with 32 books per shelf and 5 shelves on a wall. Everything is then organized into hexagons with 4 of these walls in each. What's the problem? Well, in each hexagon there's only 262,400 pages. But as we calculated before, there's this many pages in total. That's still an insane amount of hexagons needed to possibly store that many books, and to me, it doesn't feel like I'm exploring the library at all. It feels like I have to type a novel's worth of a hexagon number in the beginning, and then make a tiny, insignificant choice about which of the remaining books I want to read. So to fix that problem, I wanted to make my own version called Archives of Pandemonium. Here, each decision you make is of equal size. To figure out how many numbers you should choose between each time, and how many times to do it, let's analyze what we've got. Essentially, Library of Babel outputs pages that are 3,200 characters long with 29 different symbols. We'll call the amount of different pages that exist the output space, which can be calculated by saying 29 to the power 3,200. Now, to make each decision the same size, I decided to use this format, 10 letters and then 16 numbers. That's this many different options. With that, you'd have to make a choice 155 different times. I thought that was a bit too much, so I decided to make the output into tweets instead of books, so that each message outputted would be only 160 characters long with 32 different symbols. That makes some of the math prettier. That's this many different tweets, and that means you only have to make a choice 8 times, which is much more manageable. From there, I basically made up some fiction about what each choice represents. The address of a train station you want to go to, or the floor you want an elevator to take you to, and so on. At the end of it all, having taken a choice 8 times, you have a binary number which is 800 digits long. Now, we want to do some kind of math to it, to make it into another number. If we were to just convert this into letters right away, it's like the Enigma scenario with the normal typewriter. Exactly what you put in is what you're gonna get back, so browsing the messages wouldn't be interesting at all. You see the first message and it's all A's. Go to the next message and only the last letter will change from an A to a B. The idea is that all possible messages exist somewhere, but that they're sort of scattered around. So let's talk about how to do that with what I call the Babel algorithm. To make the messages feel shuffled, we need to somehow take the 800-bit number we get in and convert it into a different number. The manner in which we convert it is called an algorithm. We can say 3 things about the algorithm. 1. The output should be completely unrecognizable from the input. 2. Changing 1 digit in the input should completely change the output. And 3. The algorithm should work both ways, so we can do a search. As a commenter named David Coleman mentioned on my last video, the criteria I've described here are actually a perfect fit for a normal encryption algorithm, such as the Enigma machine. The output should be unrecognizable so that no one can read your secret message. A small change should completely change the output so that no one can spot patterns in the secret message to sort of stitch together what the input might have been. And of course, the algorithm should be reversible, otherwise you've just sort of crushed your data and lost it forever. So at this point, we could use a standard encryption algorithm such as AES, but I wanted to make my own version. This way, I could be sure that I take 800 bits in and put exactly 800 bits out. Of course, it's not going to be cryptographically secure, but that's not important for my use case. So from now on, we're mostly going to be talking about how I messed around until I got an algorithm that worked for me. To make my examples easier to understand, I'm going to be talking in regular base 10 numbers, but keep in mind that all of this actually happens in binary. So to make sure the algorithm is reversible, we need to make sure that we don't lose any data by having collisions in our outputs. To explain this, imagine an algorithm that's just take this number and output the number 8. No matter what we put in, we would always get the number 8. That's a huge collision, and because every number outputs 8, we can't figure out what it was originally. In addition, if the output space was smaller than the input space, you're guaranteed to have at least one collision, sort of like how trying to fit 10 pigeons into 9 holes requires you to put at least 2 pigeons into one of them. I guess that's why it's called the pigeonhole principle. If we can guarantee that the output space is the exact same size as the input space, and that no data is lost while manipulating it, we know that every input and output can be generated because the algorithm is reversible. So the way we can manipulate data is limited to ways that don't destroy it. For example, reverse the digits, or rotate the digits in the number this many times. Both of those things can be restored if you know the procedure in which it was done. So let's say that's the algorithm. Reverse the digits and then shift all of the digits 2 times to the right. That makes the output sort of unrecognizable. 25,184 becomes 52,481. But since we do this in exactly the same way for every input, changing one digit still only changes one digit of the output. For example, 25,184 becomes 52,481, but 25,185 becomes 52,581, which looks suspiciously close to 52,481. That's a problem, because it fails our second criteria. We could try this. Count up all the 4s in the number and use it as a seed to a random number generator. That means the random number generator produces the same results every time. Then, use it to randomly generate a list of operations to do in order to shuffle around the digits. Now, when we put in 25,184, we count 1 4. We still get 52,481 like before, but when we change the 4 to a 5, now there's no 4s. So instead, let's say we shift the digits 3 times to the left and then reverse it. This gives us 15,258, so this looks good, until you realize that the next 9 numbers also have no 4s in it, so they will again look pretty similar. While thinking about this, I thought about how, ideally, I'd be able to take all 241 digit numbers and pair every one of them with some other random 241 digit number, in a way that ensures that each number is only paired to one other number. Of course, this is what we've been trying to avoid all this time, since it would require storing each one of them. However, I could split the number into chunks of, say, 4 digits, and then have a table with every 4-digit number randomly paired to another 4-digit number. Then, I could have 10,000s of these tables, each with a completely unique way of pairing up the numbers. Let's say I have the number 271,200,050,010. I start out by looking in table 0. I take the last 4 digits of the number 0010, look them up, and then substitute them for 4,864. Now, I also remember that number and pull up table 4,864. Here it says what I should do with the next chunk of numbers 0005. It's 5,590, and I repeat this process over and over. But instead of storing each of the 10,000 tables, I just generate them randomly by using the table number as a seed, just like we did before when we used the number of 4s as a seed. This is relatively cheap for a computer to do, and remember, I'm not generating numbers, I'm only using the random number generator to shuffle all the existing numbers in a random yet recreatable way. What this does is that when you increment the entire number by 1, the last 4 digits change completely, which changes which table we'll use for the next chunk, which in turn changes the entire number completely. As an extra safety, we'll still count the amount of 4s at the end of it and use the method from before to reverse and shift the digits of the number. That way, even if you change a digit halfway through the number, only changing chunks from the middle and onward, that would most likely still change the amount of 4s in the number, which ends up changing where every single digit of the resulting number is located. And that's how it works. Generate a table of every 4-digit number paired to another random 4-digit number and convert the last 4 digits. Use that number as a seed to generate a new table and take the next 4 digits, and so on. Then, analyze the distribution of digits and generate a random list of operations to shuffle them. Because the digits don't change, you can generate the same list of operations and do it backwards. As for the chunk shuffling, because we always use the resulting number as the next table, we can also work backwards there and find out which tables were used to produce the number. So because the entire algorithm is reversible, we know with certainty that every single combination of outputs exists within this algorithm. What we've just been through sort of highlights how difficult making a good encryption algorithm is. What we've made here is in no way cryptographically secure, but it is obfuscated enough to make every message feel shuffled and random in the archives of Pandemonium, which is what makes it interesting to browse. My first encounter with the Library of Babel was when I was watching Byhart's video 12 Tones, where she mentioned searching through the Library of Babel as an analogy to navigating the infinitely branching tree that occurs when writing or composing music or any other creative field. I decided to include that as a theme in Archives of Pandemonium and present it more as a game experience than a website. I hope you enjoyed and found this video useful. Cheers!